I'm happy to introduce the final two lectures of today. Let's go into with Javier Bobadilla, who was the organizer last week, who's the speaker this week, and then also Thomas Pelka. They'll give a double feature talk about Lagrangian tori at radius 0, the joint work.
Well, thank you very much. It is, yeah. So we came across SWC problem because we created some technique to produce symplectic monodromy with special dynamical properties. But then when we saw our construction, we saw tori in it. So tori that were Lagrangian with respect to our metric, and then we turned and had a look to this problem. So we come from a different angle, but as far as I am learning today, it is complementary, and I think it could lead to some interesting discussions this week. So let me. So this will be 2 talks of 1 hour, and I take it easy and start with notations and the setup slowly. So the main difference, as far as I could understand from previous lectures, is that what we do is to start with the Houdini study metric of a maximal Calabi-Yaus degeneration, and then we write down a potential by hand and create a metric that has many of the properties that the Calabi-Yaus metric is expected to have, but it is not the Calabi-Yaus metric. So we will explain why it is not. So f from x to d is going to be a Calabi-Yaus degeneration. I will assume the central fiber to this to be simple normal crossings, and I will write it as sum of mi and di. So as where di is a irreducible device. Okay,
it is also this.
Eh?
It is also this.
Oh yeah, d is also this.
You can write C, like complex numbers.
I will write C. Fine. So you take
It's
make
not
the
subject.
radius smaller as you want. So let me write C. Good. So by adjunction, so you have you can take a global holomorphic form and such that the divisor of theta is sum of I, and now mu I minus 1 di. So you see the divisor of theta is supported in the central fiber, and this well, this minus 1 is for notational convenience. Okay, and now if you take any other choice of such a differential form, will be theta prime, which is f times theta, and now then the new I prime are new I plus k, and this is f to the power k, that k and I. And now I am going to take the set of i's. So I think I want to write I belongs to some index set. And now I'm going to define the set of essential indexes. And these are the new I and the i's, such that the quotient new I divided by mi achieves the minimal value. Okay, so this is the set of essential divisors, and because of this property, this set of essential divisors is independent of the choice of the volume form that has a divisor supported at the central. Okay, when you have a normal crossing divisor, you know that you can define the dual complex. So and define some dual complex that I would call, let's say, delta D. Okay, and inside of it, we can take the essential skeleton, which is the subcomplex generated by essential indices. So let me explain some background material. So there is a proposition. This is by Mustata and Mikes that says that the topology and piecewise affine structure of the essential skeleton is independent of the model. Okay, this is so the essential skeleton is a property of your degeneration. Okay, so now, so if this is a maximal Calabi-Yaus degeneration, if monodromy achieves maximum size Jordan block, okay, and yeah, and there is a proposition of Mikes and Su that says that F is maximal if and only if the dimension of the essential skeleton, real dimension of the essential skeleton, is the complex dimension of the fibers of your family. And we will use, I think, this number n. Okay, so you have this proposition, and there is another proposition that we will use, and yeah, it's another proposition by Mikes and Su, and I think it's in the same paper. In that, if F is maximal, the essential skeleton is a topological pseudo-manifold. So this means that the singularities are in codimension too. So this means that you cannot meet this situation. So you cannot have three maximal phases meeting in the same submaximal phase. This is the condition of being a topological pseudo-manifold. Okay, so and finally I have the following proposition, and this is going to be important for us. Mikes, Su, and Yu. So let me say that all these propositions are proved by a combination of minimal model program and a little bit of Berkovich geometry. This is what is inside those papers.
So it is closed topologically?
It is closed.
So it's kind of fundamental.
Yeah. So this is a longer to state proposition, but it is very important for us. So we assume maximal. Calabi-Yaus. And admits semi-stable model. So semi-stable model means that there is a model such that all the mi are equal to 1. Okay, and this by semi-stable reduction you can always achieve by a finite base change, by the theorem of semi-stable reduction. Okay, so if you start by an arbitrary maximal Calabi-Yaus degeneration, in order to reach this situation, you make base change in the base, and then it admits the semi-stable model.
Will you give examples of this manifold, which is like not a sphere?
No, I don't know any example that is not a sphere because it is a conjecture that it is a sphere, but it is just a conjecture.
But if you're asking about pseudo-manifolds, which are not, or I think
Pseudo-manifolds that are not a sphere.
No, but for this particular, for this.
Coming from a maximal Calabi-Yaus degeneration, it is a conjecture that they are spheres, but it is unproven. So this is hard problem, and so people from the view that work in minimal model program consider this as a hard question.
So you do not assume that f(x) to c is semi-stable from the beginning when you say now.
No, I didn't. That all this can be formulated in general. So suppose that it admits a semi-stable model, then there exists a non-necessarily, let me emphasize this, stable model. Okay, so you start with one model, and then you maybe you do birational transformations and get another model. So I didn't give a name to this model. C. Oh, C. With the following properties. Okay, so mi, so I keep same notation. Mi equals 1 if I is essential. Okay. B. You can choose theta as before, such that nu I is bigger or equal than 0, and nu I equals 0 if and only if I is essential.
Can I maybe it's a stupid question, but so what does it mean subcomplex generated by is it simplicial complex?
Yeah.
Which is
Yeah. The essential skeleton is a simplicial complex. So how the dual complex is a simplicial complex. So you take all. Let me do the A3 singularity. So A3 singularity, you have 3 divisors. So now you take the simplex generated by these 3 divisors, and now if 2 of them, now you remember that in the A3 singularity, this is the resolution graph, and now if 2 of them intersect, then you mark this place. 2 of them intersect, so you have the 3. If 2 of them intersect, you mark this place. So you have to mark this, and you mark this. So the dual complex is a subcomplex of a simplex. And now the essential skeleton is the subcomplex generated by the vertices that are essential. So it is a simplicial complex.
so it is a subcomplex of the dual.
It is a subcomplex of the dual complex.
when you have two intersections of when the intersection of two components is not connected to your take several simply.
I think we do assume that they are connected. Let's assume they. So better we don't get lost in this. Okay. So and now this condition is very important one and will be used in this talk. Yeah. So maybe we need names. We need names to the faces. So so you enumerate the indexes 1, 2, 3. So this is the face delta 1. This vertex is the face delta 1. This is the face delta 3, and this edge is the face 2. So this is a handy way of enumerating the faces of the dual complex. So if delta I is a submaximal phase, so because it is a maximal Calabi-Yaus degeneration, this means if the number of points in I is n minus is n. Okay. And it's a moment of introducing a bit more notation. So you have the notion delta I, and now I will define. This will be used all the time. Di is going to be the intersection when I belongs to I of di, and di circle is going to be di minus the union of all divisors that are not in I. So just extract. Okay, and if this is submaximal phase, then di, the pair di circle is P1 C star. Okay, so this means that any submaximal intersection of divisors is a P1, and exactly two other maximal, two other essential divisors will meet this this P1, and no other divisor meets this P1. This is what this condenses. Okay, so
I don't understand B. So this new I is greater than 0, new I is also 0.
well, it is compatible. New I is greater or equal than 0 in all the vertices, and if it is essential,
Oh, the
it
second
is
thing
exactly
has a
0.
razor. Okay. I thought the equivalent.
Yeah. So it means that you characterize the essential divisors by those that where the differential form has no zeros and no components. Okay. So this is a proposition, and I want to do a very brief indication. How do you prove it? So you start with some models.
So in C, you need to assume that delta I is also essential. So the big I is a subset.
Oh, submaximal phase of the essential skeleton. Submaximal always of the essential skeleton. So the proof of this theorem proceeds as follows. You start with a semi-stable model. You run a minimal model program. You get by rational transformation, some minimal model that may have some singularities, but those singularities happen not to touch the submaximal intersection, and then you do some resolution of singularities. And the difficult thing is to prove that all these steps will lead you to this proposition.
But isn't that equivalent to say that the delta S is topological to the manifold?
No, you wouldn't know, for example, that this is a P1. You don't know the
Ah,
genus.
so B is exactly partial.
You don't know the genus. So what time I started? I lost track of time, and I think I want to analyze it. How fast?
We started a little later.
Maybe 20.
Okay, good. So I have done 20 minutes. Very good. Not so bad. Okay. Yeah, so
We started at 20.
20.
One more time.
Let's say 25. They I promise not to take too much time. Okay. So now I'll give some preliminaries on the Calabi-Yaus metric. I think everyone knows. Perhaps if you get bored, you can tell me to go faster. But this is cross community, so I decided to be friendly to everyone. So so in this talk it's very important to define this function. Absolutely important. So you define t as -1 divided by log of the modulus of f. And now you choose the omega that appears and the theta. You choose the theta. You start by the theta that appears in this theorem, in this proposition, and you define omega is theta, and you divide it by the logarithm, the derivative of the logarithm of f, and this this omega set is going to be the lower section of the canonical bundle, and it's nowhere vanishing. This is a Calabi-Yaus form. Okay, so we start this Calabi-Yaus form, and the divisor of omega has coefficient 0 di. Oh, yeah, essential. Okay, and now I will define a new volume form. So let me define one volume form where I will take. I want to be a little bit careful with scaling, so I take t to the power n, and now I take I divided by 2, n minus 1, and now is n minus 1 divided by 2 omega wedge omega bar. Well, if you take omega wedge omega bar, you obtain a real volume form, and I just rescale it. Well, I have to put this I because I want it to be real, and well, yeah, just take this rescaling, and this volume form has the property that the limit when z approaches to 0 of the integral of xz vol nu is finite and non-zero. Okay, so I am using this volume form, and now I will state Yaus theorem. And Yaus theorem, so I started with a model, and since I start with a model, I have a Fubini study metric. So let me throw the Fubini study metric into the model. And this total space is smooth. Yeah, otherwise it's not simple normal crossings. So I can write that there exists a unique potential for each point that is I'm going to call the Calabi-Yaus potential at C, such that I define omega Calabi-Yaus C as omega Bubunius to the Z plus the dc of the Calabi-Yaus potential, and then this is Ricci flag. And Ricci flatness, so Thomas is going to use this equation, is characterized by the complex Monge-Ampere equation. So what you have to write is omega Calabi-Yaus Z to the power n is some constant C of Z vol nu. This is the complex Monge-Ampere equation. And the scaling have been picked up such that the limit when Z equals 0 of C of Z is finite and non-zero. Okay. Yeah, this is yeah, and now what was coming in my talk is the statement of Kontsevich and Soyerman conjectures, but they have been stated by Joel. No, Jacob. By Jacob. And so I will skip that part because we got sufficiently good in, we got a whole lecture. So you know the feeling, what needs to be proven. There is a Gromov-Haudsdorff conjecture, so we want to understand what is the Gromov-Haudsdorff limit. So we want to understand the Gromov-Haudsdorff limit of xc omega Calabi-Yaus.
I don't think I mentioned the Gromov-Haudsdorff limit.
Well, I'll mention that.
One question, like the fact that the volume remains finite. Does this have to do with the fact that
You
it's a maximal degeneration, or
No, you always can scale.
yes,
You
but
can divide by the total volume.
so you're fixing
So I just found what is the scaling that you need.
yeah,
and
but
that's
it is connected, right? The fact that you have t to the power n is because
The fact that there is an n, that it is precisely t to the power n, has to do with maximal Calabi-Yaus degeneration. Otherwise, you would have to pick a different exponent. But this is let me not deviate. I can explain after the talk with you.
May I just make one remark?
Yes.
It's not only considered someone's conjecture. Gross and Wilson had sorry?
Right.
Gross and Wilson had actually a paper proving it for K3 services and simultaneously and independently conjecturing it.
Okay.
So the only thing, I mean, consider someone just kind of waved their hands, but actually Gross and Wilson proved something and had a kind of foundation for the conjecture. And now everybody is saying this consider someone's conjecture. I find it unfair. I think we should
Well,
also
probably
be a
it
little
is,
bit
and
more
we were
careful.
not completely aware of this, so we
Yeah,
changed our
look up the
formulation.
Gross-Wilson paper.
We changed our formulation. Thanks. In fact, in Kontsevich and Soyerman paper, they mention a little bit Gross and Wilson, but
They do,
like a little bit in passing. So
Right,
it's- So you from there you don't suspect.
It was
that.
before I worked with Mark, but I was actually at a conference where Kontsevich was stating this, and Mark was also in the audience. They had a discussion on that. It was shortly before the Gross-Wilson paper came out.
Yeah. Anyway, what I am going to state is our main results at this moment. So we will need Kato-Nakayama spaces, but by now, let me call C log the real oriented blow up. Okay, and now what we do? So we construct a locally trivial vibration. So the real let's do a picture. This is C. And for C log, you have to replace the point by S1. Just being serious in taking polar coordinates. So we find a locally trivial vibration that I'm going to call it A. C log. Of course, C star is embedded in C log, and on top. So what we do is to erase the central fiber and compactify in a different way. And we compactify in a different way such that this, in a natural way, is a C infinity trivial vibration. So this is not the Kato-Nakayama construction of the divisorial log structure. We have to do something else, and this will be the main content of this talk. This is going to be called a Campo space. This Campo space has a blowdown map pi to X. Okay? So we construct this space and we construct a family of potentials. So we construct phi Q. Is a family of functions that are defined in X cycle times 0, 1 to R, and Q phi. So I think it's better to write like this, so there was confusing. Q belongs to the interval 0, 1. We construct a family of potentials with the following properties. So once you have a family of potentials, you want to define WQ, and WQ is going to be pi upper star omega X. So I call omega X for the rest of the talk what I call Rubinian study. Okay, so this is the Kahler form that projective geometry gives to X. And I will write D, C of phi Q. Okay, so I define such a sequence of functions with the following property. So with the following properties and some more that will appear in the talk of Thomas. So I will state those properties that concern the family X circle itself, and there are further properties that concern the Campo space itself. At this moment, I think it's convenient to do some spoiler. What we are going to do is to construct Kahler forms in the open part that extend to fiberwise symplectic forms in the total space of this C infinity trivial vibration. Then we look at radius 0 and we write down the formulas of our forms. And because pi is crunching a lot, the DDC phi q is going to dominate over pi lower star x. So we get very canonical formulas for the symplectic form, and we see Lagrangians that come from the Kato-Nakayama construction. This Campo space dominates also the Kato-Nakayama space. So the tori that appear naturally in the Kato-Nakayama construction appear to be Lagrangian in radius 0, and we move them to positive radius by the symplectic connection. So this is the summary of what is coming. And so it is important that whatever this form is doing extend to the whole A. But now I am stating, I want to give you the feeling of what these forms are doing with respect to the original Calabi-Yaus. And you will see that they share most properties that are expected for the Calabi-Yaus metric, except for one. So let me let me explain the.
Can I ask just one?
Yeah.
So you say that the fiber at every point over this blow-up circle is diffeomorphic to the.
It is.
But it's a smooth family.
It is a smooth family. Same thing. Okay, so.
May I ask one question?
Sure.
I'm very interested in these kind of geometries in a different context. So there's a central circle. Yeah, there's one over the origin or whatever you think about it. And do you know do you have a good control of the symplectic geometry around this circle?
Very good. So we know precisely what is the symplectic monogram. Very good control.
I'm very interested.
Very good control. So it is as simple as you can. Well, I can say in 2 words what it is. So everyone studies a Campo model for the monodromy. It is the same thing, but it is symplectic.
Great.
But again, like the total space is smooth, SNC, and you start with a killer for all that.
Yeah.
So your things are not, so his things are not directly included. Toric degenerations are not an example of the setup before you resolve the singularity.
Not yet.
No, but I think the models are the same except for the fiber, for the central fiber. Same.
You were saying that the models you get from toric geometry, the way I wrote them down, they're normally not smooth in total space. Yeah.
Yeah. Well, extending to toric singularities is challenging. Last year we were working for more than a month, and so there are non-trivial aspects in extending this construction beyond the simple normal crossing case. But we don't think it is impossible. We think that it is technical.
So the formulas that you will write do not work, that we know.
Yeah.
if you just copy them blindly, they will not work.
Yeah. The blind generalization creates problems. Okay, so let me state the properties. So A, let's say WQ restricted to XC is Kahler for all C belonging to the circle, and Thomas will explain you where it is symplectic. At radius 0 for some Q's it will be symplectic. There will be one special Q in which.
But please,
Anyway.
C star, not D0.
Oh.
D is the central fiber.
C is. Thanks. B. There is a region, and this region, there is a region that I am going to draw. Let me call it A. N. Inside. Okay. And this region is a codimension 0 sub many with boundary and corners. So I'm going to show you codimension 0 sub many follow the plane. This is what we mean. It's just a domain such that the boundary is a manifold with corners. Okay, and such that now if you define X set M, okay. I forgot. I have. Okay, so at this stage I have to do something. I need to define the expanded dual complex. So let me do it in. So I'll do 2 examples, and then you understand the general case. So let me start with imagine that in the expanded essential scale. So let me start by this, which is the essential skeleton of the Fermat cubic degeneration. The expanded essential skeleton is this. So each point you replace by a small interval. So you create a little bit more space. Okay. And now, if you start by this simplicial complex, you are going to erase the codimension 2 part. So make a hole in the codimension 2 part. And now each of the submaximal faces you replace. You put some interpolation interval. And you have to do it in all of them. Okay. This is a procedure that can be done to any simplicial complex. So this is the expanded essential skeleton. And there is a fibration. There is a fibration to the expanded essential skeleton. And I'm going to call it LS. Locally trivial fibration. With Lagrangian torus fibers.
So this is not closed anymore, right?
No, it is not closed anymore.
So you have gaps in the corners.
Yeah, this you don't fill with anything. Because anyway, we don't know how to continue. We don't know how to deal with the singularity, so we don't know how to continue this fibration to the interior. So the next paper, we will see what to put there. But what we could achieve, we just don't care. We only need this part.
Okay, may I ask in the expanded essential skeleton, what do we put in at the corners, at the vertices?
You put nothing, you leave the hole.
Oh, okay.
Just leave the hole. So the only thing you do is to put a little bit of interpolating. This is the most beautiful example because
This is misleading. Misleading. One dimension is misleading.
What?
Misleading. One dimension is misleading because you don't have the.
It's misleading, but it illustrates something. So in this cubic degeneration, it was said that most of the volume accumulates close to this point when you degenerate the Calabi-Yaus metric. Well, the faces of the essential skeleton correspond to these points. And this small interpolating piece, so this should be pictured small, not like I did. This small interpolating piece corresponds to the submaximal faces. So the submaximal faces are P1, C star. They are P1 and 2 mark points. And when you have P1, 2 mark points, there is a unique radial coordinate, a unique angular coordinate. So these interpolating pieces correspond to the radial coordinate of P1 minus 2 points, and it will be apparent in Thomas dock. So this is the role of the expansion of the essential skeleton.
Do you expect them to somehow shrink in any
They do.
They-
Now I'll write the metric aspects, and they do. Okay, see. The Gromov-Haudsdorff limit, when z approaches 0 of x z, and now I do x z minus the smooth part, is the essential skeleton, but not expanded, just the essential skeleton and essential skeleton, the part of codimension. So this is exactly in line with, well, probably with Grossal Wilson, but we didn't read this formulation with the formulation that appears in Kontsevich and Soberman. It says precisely this. So there is a codimension 2 part in the integral affine manifold, and this Gromov-Haudsdorff limit needs to
Do
satisfy.
you know anything about the metric on the open faces? Like, is it a flat metric or?
It's not, it collapses, but it collapses down to zero. If you rescale this metric to finite radius, asymptotically it collapses down to zero.
No, you are asking about open faces, right? So
Yeah.
the metric on the essential skeleton.
In the
This
open
is
faces
the-
of the essential skeleton. Yeah, I'll tell you what is the metric. This is the usual Euclidean metric. So this is embedded in the space, and it has a usual Euclidean metric, and the Gromov-Haudsdorff limit is this with the usual Euclidean metric. Okay, so
I'm a bit confused actually. This codimension 2 seems to be completely different from everybody else with codimension 2 part, which you have to exclude. Like in theirs, you have to exclude like midpoints on the interval of the edges of this.
But I think there is like maybe not 100% consensus. I think Niklas and Shu have made a similar construction where they exclude codimension.
now let me answer your question. You're concerned about this example.
I'm just concerned with the
Yes.
integral affine structure on the boundary of the simplex of the dimension.
So if you consider this example, you'll have the, as you say, in the middle, you have the. These are the points where the singularities accumulate. But this is not example. This is not example that we consider because the total space for this degeneration is singular. So if you want to get a smooth space and simple normal crossing case, you need to blow up the Weil divisors. You can blow up the Weil divisors, and then the singularities get pushed into the middle of the divisor. The singularities of the SYC will get pushed to the part that we don't see here.
I thought you were going to say that somehow when you resolve these singularities, you will get that the essential skeleton has a lot more faces, and
The
those points you
essential
draw.
skeleton has the same number of faces because they are small resolutions. You are blowing up the Weil divisors, and
Yes.
so what you do is to destroy. You destroy the toric structure of the divisors, and so you don't have a torus action. You cannot create those tori anymore.
Maybe it's important to add here that XZ is considered with the metric coming from omega Q, and both Z and Q go to 0. You didn't specify the metric which you are collapsing, and it's not the Fubini study, of course, because it cannot be.
Of course, it
studied,
is not a Fubini study.
and
It
it's
is
not Calabi-Yaus
omega.
because we cannot deal with it. So
It's omega Q
yeah, and Q depends on Z.
and Q.
Still there.
And Q. This is already for admissible.
Yes, you need.
No. With Q, when Q is finite, the Gromov-Haudsdorff
No.
limit was the same. Do we use that Q goes to 0?
Yes, we do, because you need flat metric on the faces, and if Q is positive, you don't have flat.
Right. Otherwise, it is not with this metric.
Yes.
The topological space would be the same, but the metric wouldn't be flat.
I also don't understand where in the statement you say that the symplectic structure extends to the exceptional circle. Where in the statement do you say that?
I didn't say it yet, but Thomas will say it. There is another hour. I said that Thomas will say how it extends. I didn't say it, and I will not say it.
I have a trivia question. When you say usual Euclidean metric for a simplex, how do we embed the simplex? So like symmetrically, like the convex hull.
You take the usual simplex that
Well, they're
you learn. Well, I take this one. This is the two simplex one.
okay,
And
which
so
is
on.
not fully symmetric.
No, that's kind of true. So there's some. The simplex is not better than others,
Well, in Euclidean geometry,
but in different metric.
Yeah, that's
So
why I'm
to-
asking.
to-
So which one that is?
I am taking this one, is precisely this one.
Which one is which one?
So you take
What is
you take the following simplex.
Seems to be some
Delta
asymmetry.
n is the set of points in R is in Rn plus 1.
Oh, and R plus 1. Okay.
You're taking
so
Rn
what's
plus
M?
1.
Sorry.
Oh, there was the one simplex you drew.
Yeah, this,
Sorry.
Not the one.
this is the simplex. It's completely symmetrical.
Sorry.
I'm happy.
So is M the number of components in the central? Is M the number of essential components, or
M is
What-
the number of all divisors.
Yeah, M is the number of, but he asked for the definition
all
of the simplex. So
divisors.
we take the usual simplex by taking sum of wi's equal to 1. And wi bigger or equal than 0.
so then I have one more question, if it's okay. So to what extent do you think these potentials you create phi q depend on the model?
They depend on the combinatorial structure of the central fiber.
In the model, yeah.
Yeah.
And not just on, say, the essential.
And this is asymptotic. Well, let's postpone the answer to this question after the next talk of Thomas, because it will be completely apparent.
Okay.
Because the construction is absolutely explicit. We write down the formulas. So there is no step that is existential or something like that. Yeah. This is a good question, and let me make it clear. So you can take the base of the vibration, the C log, and then you multiply by 0, 1. Z belongs to here, Q belongs to here. And let me forget about the angular component and draw like this. This is the Q, and this is the Z. So as Z approaches 0, you need to pick a path that comes to Q0.
You know what the path is.
Any one will work. Any path will work. As long as it approaches C. For the statement C. Now, when I say further statements, then I will give a small restriction on the path. Okay. Yeah, and this gave us headache. It is a bit more convenient to write Q, and here you write T. Anyway, you know that T is a rescaling. So if you picture with the T coordinate, everything is a bit more comfortable. It's just a rescaling of one axis. Okay, so this is C. So let me proceed. And I should somehow press a bit because I promised Thomas to do a bit more than I am doing. So the limit again C approaches 0 and Q2 that I don't remember at this stage, but what I want to add something that is true for sure. Now I will introduce another region. Okay, so this approaches 1. So this property is called volume filling. And what is this region? What is the generic region? So you have the fiber, you have the smooth region, and you have the generic region. The generic region is the one that Jan Lee considers in his paper. So you have a vibration to expanded essential skeleton, and here you can take the union of the open part of the maximal faces. So these are the tori, the union of the tori that are on the maximal faces. This is, and already the volume in this region, in this region, fills the volume if you compute in an appropriate way. You compute with respect to the volume that you have to compute that is the Calabi-Yaus volume.
What is this omega?
Omega I introduced before. So you have the
it's
holomorphic volume form, it's the Calabi-Yaus form.
So the dependence on Q, where is
Q is a parameter, so that you have a one parameter family of symplectic form.
but a priori, is there any relation between these
With the omega and the Q? No.
Ah,
No, there is no relation. Okay. So now asymptotic Ricci flatness. In the degenerate region, and it is as follows. Yeah. So let's see. Yeah. You take omega. So now let me take a path. We call a path admissible if it is not like this. The path has to go to the origin. The path is admissible if it has like finite slope. Okay. So if you have an admissible path, now Q of h to divide is C of h times vol omega nu, and the limit when h approaches 0, C of h is positive constant. So the complex motion per equation is writing this with a constant. So as you come closer and closer to 0, then the variation, so the deviation for the complex motion per equation gets smaller and smaller in the generic region. And now there is a final.
Sorry, what's H here?
Oh, H is so gamma of H is set of H, Q of H.
Okay.
This is gamma of
yes.
H. Okay.
Parameter.
Sorry, I didn't say the parameter of the path. Okay, and now the asymptotic Ricci flatness, and now there is a property of asymptotic specialty of Lagrangians at the generic region. And as before, you take a path like this, and now if you take a Lagrangian in the generic, so the exact formulation is that there exists an element in S1 such that now if you take the imaginary part of omega Q of big omega at the Lagrangian, theta times omega, and you divide by the real part of theta times omega at the Lagrangian, this approaches to 0 as h approaches 0. So the speciality condition is that the imaginary part of the omega is exactly 0. this is a special with phase 1. So there is a generalization, is that you may put an element in S1. So we need that generalization. So this says that the Lagrangians are the generic Lagrangians are the Lagrangians in the generic region are asymptotically special. This implies that all Lagrangians have trivial Maslov class, so you can do Floer theory with them, and it implies that they are asymptotically, so the volume is minimal in the homology class in an asymptotic sense. So this is the statement of our results, and now what to do? So I exhausted 1 hour. I leave you all the Acampo space construction, and so I didn't fulfill my promise to Thomas, but I think I made you understand.
Let's thank Javier Fernández.